up, down, left, and down,
Right.
right, or whatever, something. I don't know. Whatever, however you do it.
We'll get to up and down a little bit later. You can do this without up and down right away.
Okay. Well, what I meant is that once you start talking, well, maybe forget it. Forget it. Well, so what you could store with each of these things is the path that you take to put it where it belongs, I guess. But it just seems like it's going to be very inefficient if you're trying to.
Yeah, the up-down representation is more efficient. Yes.
Okay.
In the hackage, they have an API with treeloc that has the tree, the lefts, the rights, and the parents.
Are you cheating?
I'm cheating. Well, we seem to be a little stuck. So.
You guys want me to just walk you through the package? How they end up doing it?
Part of the problem is that the letters and stuff are all flying off the right side of the whiteboard.
Oh.
The picture is sort of.
Sorry. I can redraw it.
What?
Yeah, can you use the
Picture fell
darker
off the
marker
right
that
side of the
is
whiteboard.
not exactly readable?
Where is the purple?
It's right here.
Store it tit side up. So.
No.
What happened?
You erased the picture.
We'll find out.
I was going to redraw it. That's a pretty easy picture to remember, too.
Are you sure? I'm pretty sure I've forgotten what that looks like.
What I'm confused
It
about
was
is
3
parents.
levels,
How can you have
binary
more than
tree,
one parent
A
in a tree?
through
You can't.
whatever.
Well, no. Sorry, different story.
Parents. It's ancestors. Maybe it's ancestors.
Oh, okay.
So for
Ancestors and
D.
parents.
Yes.
I guess that makes sense, maybe.
Yes.
What are you saying, ancestors?
Like the parent of the parent is a parent also.
grandparents.
Alright, so when we
The
take
family tree
A
line.
and we put it
Right.
on the left. Okay. So now we're left with this forest B, C. And what we probably want to have done, when we took A off, I think, we want to have labeled B and C, attached to B and C, where they go, I think. So
some kind of.
So essentially, since this is a rose tree, it's going to go that way, and so not an A, because A
Okay.
is just a label, but sort of a.
I'm just using it to name the node.
But I guess the first level it's going to be very weird and special. So it doesn't at the first level it's not going to make any difference. So let's see what happens when we get to the second level, which is that we're going to take off B, and now we have to
Do something with D and E.
So we're going to stick B where it belongs on the left, and now we have to label D and E. So what we have to know about D and E is that to get to them, we're going to have to go left from A to find their parent. That's the point. So D and E are going to get labeled L and L, and so now we take those D and E, those labeled D and E, we're going to move them over to the right, correct?
So you're just
And you have
keeping
to see for
basically you're keeping a history of
something like that.
all the L's and R's that you took to get
Something
to that
like
point
that.
on all the things in
Well,
the
L's and
right.
R's aren't going to work.
We have to
I'm
know
not
the
clear
parent.
about
It's a
your
rose
data
tree,
structure
right?
on
We have to know the
side,
parent
but,
specifically. We can't do Eleanor,
Oh,
right?
We'll start with Eleanor,
Okay.
and then we can
So
tackle the
then,
case with more children.
then we have C, and we stick C where it belongs, which is to say at the end of the child list for A, and then we're gonna label it, and we're gonna say, well, I guess we're gonna actually label those, we're just gonna be like, we're gonna label them 1, because
Yeah,
we're gonna
you could do
change
that
the
too.
L
You could-
to a 0, and we're gonna change
Right.
Yeah. And so we're going to label those 1. And then these children, they're going to be, children are going to be, it's going to be a list of...
It's going to be a list of numbers.
Of
yeah,
numbers.
It's going to be the list of the...
Yeah.
So it's going to be pairs, right? We have the node, and then we have its label.
It's a list of
It's-
numbers,
yeah.
Yeah, rose trees were too complicated.
It's what the other like basic trees or basic zipper example I could find. We could do binary trees too.
Anyways,
I think- wouldn't-
doesn't matter.
Pre or post order be...
Okay. Show me for your post.
Yes.
Finally.
Just
The
because
reason I'm saying we should do this is because I just want this is the most important thing is just getting an idea for how these traversals get turned into zippers, and then watching Lens do it magically from the code of the traversal. Lens will just take a function that does a traversal and do the conversion to a zipper.
It's so one-dimensional.
What is?
the traversal.
Foldable and traversable,
Yeah.
they're just...
Is
very
that kind of the point?
one-dimensional.
Yeah.
Pre-order does sound like it should be easier though.
Because you can just, it's like you
It's like you,
you
wait
deal with
for-
the whole thing once
Yeah.
you get to it.
You wait for the specific case you care about, and that's when you. Yeah.
You labeled them wrong.
A, B, C,
No, A, B.
Well, if
should be C.
Oh, you want me to label it in pre-order?
Yeah.
Wait, what?
He's labeling it breadth first.
he's labeling it in the order that we should
Oh.
take the things off.
That was right.
You didn't have to do the A and the B.
Okay, where are the labels going?
A, then B over here, and then C down at the bottom.
All right.
Yeah.
Okay, so now when we're on a level, like if we're looking at B,
Okay.
we just have a zip list, as you said, of the things before it and after it on that level.
Okay.
Zip list?
A zipper of a list.
Oh.
That's what I meant. And okay,
I think you lost me already.
I think I lost myself.
Let's stop there.
No confidence this is easier.
I didn't say it was easier.
Okay. I was
Anyways,
Ben.
so
I
let's
think
go
Ben
on
was
to-
implying that was easier.
I thought it would be easier.
So the other thing I want to talk about is what this is actually used for. The most basic thing it gives you is a way to represent paths through a data structure, which becomes a form of indexing into that data structure. So if I say go left, go right, go left on the same data structure twice, I get the same value, and that becomes a kind of index into that data structure. And it's distinct from go right, go left, go right, and any other combination, right? You get the exact same output. We can actually use the list zipper stuff we just wrote to mess around with this and see that that's the case.
I believe you.
Okay.
So you're saying this is for lists?
And trees,
And
depending on the traversal you use. So depending on the data structure you start with and the traversal that your zipper implements,
Right.
this is true.
This is what David was saying, that it's one-dimensional.
Yes. This is the advantage is that,
You can just go left and right.
yeah.
I'm not sure what you're saying. Are you saying that those two are equivalent, or?
No, I'm saying they're distinct. They're separate indexes in the same tree.
Errors.
What?
Because they have different errors.
Yes,
oh,
they
wait,
have
a
different-
tree. I'm sorry.
Because one of them is like negative
Sorry.
1 and then one of them's
Confused.
1.
Right.
You're assuming we're starting at the top of the list. What if we're in the
It's a
middle?
tree.
Yeah, this
Somewhere.
is about the ordering. It's the level versus pre and post order.
But you're
stuff.
moving direction.
I'm just saying, like, go left, go right just kills itself. So it's
Right.
just go
Those,
left.
yeah, and then you end up.
Unless you're at
Right,
the end.
right.
So
Right.
essentially, I mean, you can. I mean,
Those are probably bad examples
can
to
you?
go with.
I
but,
mean,
like,
essentially, can you drop these two off, and then you're just saying?
Oh, I see what
it's
you
the,
mean.
it's
Yeah.
the
that works too. I was just writing something up quickly. I
Right.
didn't really think through that this cancels. So if this was go right, go right, go left, and go left, go left, go right, or
Right,
that still
they just don't
cancels.
say
Yeah.
cancellation.
Basically, go left is different than go right.
Right.
You just count up.
It's boring when you're doing it at
Since
compile
you-
time
since
because
you
you're
have
running a
two
text
inverse
editor.
operations.
Right.
They're almost inversive.
But the more
Kind of
useful,
Why are they almost inverses?
Because if you're at the end of the list, and
Well,
you go left, you
okay,
get bumped off.
Okay, that's true. So.
the more useful use case is for interactive editing when you're getting input from the user and you don't know which way the user is going to go. Let's say you're editing a document and you want to store it as one giant list of characters for some reason. Now you can have a cursor into that editor and still be able to track where you are in the thing, in the list of characters and what's around the character you're editing and whatnot. If you want to be able to do like spell checking, you're going to need to start putting the words and characters into some kind of tree structure. So you would probably want to be able to track where you are in that tree while maintaining the order while the user is editing. Any other data structure at all that you want to throw in there? Or maybe you want to track the list of edits that the user is making so you get a history out. So undo and redo come for free. And so that's really what I wanted to get at, is that zippers kind of track the history of edits that are being made to a data structure. And I'll talk later about how we can save those that history off and replay it. One really, really important case, this is what actually introduced me to zippers, is the use case of a web browser. If you use list-based history like most web browsers do, you end up with a situation where you have two lists, the forward list and the backwards list. And when the user hits forward, you go down the forward list. When the user hits backwards, you go down the backwards list. And that's that. Except we just implemented that. That's exactly a zipper, since the current page is the cursor and whatnot. But you can also get a tree-based history if you work with the tree zipper, right? Each time the user clicks a link, that creates a new child, and when they traverse down when they go from the next page to a new link, that becomes a new child, and you just keep going down, and when they go back, you go back up, and down a separate tree if you need to, and you still maintain the whole history. That becomes really difficult to manage mutably, I've found, unless you use a zipper. The minute I tried doing a tree-based history for a web browser I was working on, and I tried to do it by hand, and it was really, really, really painful. And then I was like, oh, zippers. Wow, that's easy. Because the Rose zipper package already had all this stuff built into it. So that's the first, I was hoping, hour. I don't know how long that actually took. Looks like an hour and a half. Well, we got here at 7, but...
Yeah, it's actually from recording time. It's been about an hour.
Okay.
It's been an hour and 7 minutes.
Yeah. So, questions, comments, concerns? This is the bulk of the talk. The rest of this is just taking this idea and adding stuff to it for fixing some of the things you guys have already pointed out. Like, for example, we can fall off the end of the list. This is also a good place for a break if anyone needs water like me.
Yeah.